Okay, continuing with limits. This is the informal definition of a limit. The notation, the limit of some function f of x as x approaches c equals L. It means that as x approaches c, the value of f of x can be made arbitrarily close to some number L by choosing values of x that are closer and closer to c. Now, the reason I call this the informal definition is because if you took a calculus book or calculus course and you would be given a definition of a limit that's called the epsilon delta definition of a limit, and that's a lot more complicated to follow and a lot more difficult to prove that limits exist using that. But since this is business calculus, we'll forego that. Now, if you read this next paragraph, it says, if f of x approaches the same number from either side of c, then we say the limit of f of x as x approaches c exists. However, if f of x approaches a different number from one side as the other side, then the limit does not exist. Also, if the limit approaches infinity or negative infinity, the limit does not exist. Now, if I say a limit equals infinity or negative infinity, it still does not exist. That is just a specific way for it not to exist. And the reason I say this is because even if a limit approaches infinity from both sides, it still doesn't approach a real number. So for it to exist, it has to approach a real number. Another thing to remember is that the value of the function at x equals c has no bearing on whether the limit of the function as x approaches c exists or does not exist. And you saw some examples of that earlier. Now, the examples above were selected for a reason. Many limits can be evaluated using direct substitution, as you'll see. But you must be very careful when you evaluate limits in certain cases. And I'll discuss these cases after we talk about some properties. Okay, here are some properties of a limit. Let's say b is a constant. Well, the limit of a constant as x approaches c is always the constant. So if I said, what's the limit of the constant function 5 as x approaches, and you can pick any number you want here, but as x approaches negative 2, it's going to be 5. If I say, what's the limit of 5 as x approaches 10, it's going to be 5. So remember that property. Now, if we have the function x, the function y equal x, and I say, what's the limit of x as x approaches c? Well, that's going to just equal c. So if I said, what's the limit of x as x approaches 15? Well, guess what? It's going to equal 15. And if I said, what's the limit of x as x approaches negative 3? It's going to equal negative 3. Also, the limit of x to a power as x approaches c is just going to equal c to that power. So if I said, what's the limit of x cubed as x approaches 2, that answer is simply 2 to the third power, which is 8. If I say, what's the limit of x to the fourth as x approaches negative 3, then that's going to be negative 3 to the fourth power, which is 81. It also works with roots. If I say, what's the limit of the nth root of x as x approaches c, then that's going to be the nth root of c. Now, it might be a nice round number, like if I said, what's the limit of the fifth root of x as x approaches negative 32? Well, that's going to be the fifth root of negative 32, which actually is a nice round number, negative 2. But it doesn't have to be. Like if I said, what's the limit of the cube root of x as x approaches 7? Well, then that's just the cube root of 7. I mean, of course, it has a decimal approximation, but the exact answer would be cube root of 7. So you can look at these practice limits down here and see if you can evaluate these limits. The answers are given. Freeze the video if you need to, then work the limits and check your answers. Okay, here are some other properties, but they're really operations on limits. We're going to assume here that b is some real number. Well, the limit of b times f of x as x approaches c is actually b times the limit of f of x. Now, how does that work? Well, it works like this. Let's say you wanted the limit of 3x squared as x approaches 2. Well, we don't know how to do the limit of 3x squared, but we do know how to get the limit of x squared from the property we talked about. We can actually put the 3 out here and say that's 3 times the limit. And now we know how to evaluate the limit of x squared. We know that limit is just 2 squared. So our answer is going to be 3 times 2 squared, which is 12. Also, if you have the limit of f of x plus g of x as x approaches c, that's the same as the limit of f of x plus the limit of g of x. Or if you have the limit of f of x minus g of x as x approaches c, then that's the limit of f of x minus the limit of g of x. So let me just show you, I'll show you the difference one here. Let's say you wanted the limit of x squared minus the cube root of x. Well, we don't know how to evaluate this difference, but we do know how to evaluate each one separately. So let's write it as two limits. This would be the limit of the first function minus the limit of the second function. Okay, now we know the limit of x squared as x approaches -1 is just -1 squared. And we know the limit of the cube root of x as x approaches -1 is just the cube root of -1. And so now -1 squared is 1, and then we have minus, and the cube root of -1 is -1, so we have 1 minus -1, which is actually 1 plus 1, which is 2. Also, we have the same property for a product. The limit of f of x times g of x is equal to the limit of f of x times the limit of g of x as x approaches c. So if I wanted the limit of x cubed times the square root of x as x approaches 4, I could write that as the limit of x cubed as x approaches 4 times the limit of square root of x as x approaches 4. And we know how to evaluate the limit of x cubed as x approaches 4 is just 4 cubed. And we know how to evaluate the limit of square root of x as x approaches 4 is just square root of 4. So you get 4 cubed times square root of 4, which is 64 times 2, which is 128. It also works for a quotient, as long as the denominator is not 0, that is. So the limit of f of x over g of x is equal to the limit of f of x over the limit of g of x. Now remember, that only works if this limit is not 0. Okay, so if I have the limit of x cubed over square root of x, that would be the limit of x cubed as x approaches 4 over the limit of square root of x as x approaches 4. And we know how to calculate the limit of x cubed as x approaches 4 as 4 cubed. And the limit of x, the square root of x as x approaches 4 is square root of 4. So that's going to be 4 cubed, which is 64, over the square root of 4, which is 2. And 64 over 2 is 32. Now, you can also calculate the limit of a function to a power, which is different than the limit of x to a power. This is the limit of a function to a power. Well, the limit of a function to a power would be, you can calculate the limit of the function first, and then you can raise that result to the power. Now, that would be easier because, look, if I asked you to evaluate the limit of x squared minus x to the 5th power, well, without this property, you would actually have to expand x squared minus x to the 5th power, which would give you, maybe 20 or 30 terms. I don't know. But it'd give you a bunch of terms, and it would take a long time to do. But what I can do is I can actually say, well, that's the same as the limit of this function, so I can get the limit of this function first, then raise it to the 5th power. Now, you know how to do this. The limit of x squared minus x would simply be the limit of x squared as x approaches 2, which is 2 squared, minus the limit of x as x approaches 2, which is 2, and then we take that 2 squared minus 2, which is 2, and raise it to the 5th power, and we get 32. Similar property works for root. If I have the limit of the nth root of a function, then that's the same as the nth root of the limit. So if I want the limit of the cube root of 5x minus 3, I can actually calculate the limit of 5x minus 3 first, and then take the cube root of it. So the limit of 5x minus 3 as x approaches 5, well, the limit of 5x, you can do this, write this out a long ways if you want, but that's just going to be 5 times 5 minus 3, which is 22. So the limit on the inside equals 22, and then you take the cube root of it. So the result is the cube root of 22. And so that's basically the properties of limits. Now, it turns out that if you put a bunch of these properties together the right way, you'll find that basically you're learning that you can evaluate a polynomial. So to evaluate a polynomial, I'm going to show you the long way. This will be the long way to do it, but then I'm going to show you a theorem that actually shows you don't have to go to all this trouble. So if I put all those properties together, let's say I wanted to evaluate the limit of this polynomial as x approaches 2. Well, to do it the long way, I'd have to say, okay, well, that's going to be the limit of the first term minus the limit of the second term plus the limit of the third term minus the limit of the fourth term. And then I can write this as 4 times the limit of x cubed. I can write this as 7 times the limit of x squared. I can write this as 3 times the limit of x, and then minus the limit of 2. And of course, all of these are as x approaches 2. Well, now I know how to evaluate each of these. I know the limit of x cubed is just 2 cubed as x approaches 2. I know the limit of x squared is just 2 squared as x approaches 2. I know the limit of x is just 2 as x approaches 2. And I know the limit of 2 is just 2 regardless of what x approaches. And then so I had to take 4 times 2 cubed minus 7 times 2 squared plus 3 times 2 minus 2. And then, calculate all that out. And unless I got my arithmetic wrong, that all comes out to 8. Now, but did you notice that if you had simply just plugged 2 in to this polynomial and evaluated it, you would have gotten 8? Because that's exactly what would have happened. Well, it turns out, since we have all those properties, to evaluate the limit of a polynomial as x approaches c, all we do is evaluate the polynomial at c. So I don't have to do all these steps up here. If I want the limit of a polynomial, I can just plug the number in, see, like I'm going to do here. If I want the limit of x to the fourth plus 2x squared minus x plus 5 as x approaches 2, just plug a 2 in everywhere for x. So I would get 2 to the fourth plus 2 times 2 squared minus 2 plus 5, and then when I evaluate that, I get 27. Same thing is true for rational functions. As long as the denominator is not 0, if I want the limit of a rational function, I can just plug the number in. So, for instance, if I want the limit of x squared minus 5 over x plus 3 as x approaches -1, well, I know -1 doesn't make the denominator 0, so I can apply this theorem. So just plug -1 into the top, plug -1 into the bottom, and evaluate it. Well, if I plug -1 into the top, I get 1 minus 5. If I plug -1 into the bottom, I get -1 plus 3. So that's going to give me -4 divided by 2, which is -2. And so many limits can be evaluated directly. And so here are some limits here that can be evaluated directly. Now, by just plugging in. But other limits cannot be evaluated directly, and you have to learn the little tricks. Now, for instance, this limit, if you tried to plug 2 in, you would get 0 over 0. Well, that's called an indeterminate form. And that means that the limit cannot be determined, okay, from this form. So we have to figure out a way to rewrite this function so we can evaluate the limit. Same thing here. If you plug -3 in, you're going to get 0 in the numerator and 0 in the denominator. Same thing here. If you plug 0 in for x, you're going to get 0 in the numerator, 0 in the denominator. You're going to get an indeterminate form. Now there's other indeterminate forms, like if you've got infinity over infinity, that's an indeterminate form. If you get 1 to the infinity power, that's an indeterminate form. But basically, we're going to focus next on this indeterminate form, 0 over 0. Now, one of the common mistakes that students make when I say evaluate a limit like this one here, they get 0 over 0, and they either say that equals 0, or they say that limit does not exist. Or maybe they say infinity. But the point is that anytime you evaluate a limit and you get 0 over 0, there's a 95% chance that the limit's actually going to equal a number. So just remember that. 0 over 0 when you evaluate a limit, and the limit's probably going to equal a number like 2 or -3 or something like that. So be very careful when evaluating. And I'm going to show you how to evaluate those limits that give us those indeterminate forms in the next video.